Hello everybody, this is Assistant Professor Dr. Al-Zuhairi. Today we're speaking about the finite element modeling of thin plate in bending. Analysis of plate in bending. The basic theories of plate bending and according to the nature of stress state, plates may be classified in three categories. The first category is thick plate, in which triaxial state of stress is developed and defined by a complete set of differential equations of a three-dimensional theory of elasticity. Number two, thin plate with small deflection, in which the membrane stresses are very small compared to the flexural stress that be developed under deformation due to the transverse load. In this type of analysis, the stresses perpendicular to the plate will be neglected. Third, number three, thin plate with large deflection. This is characterized by the fact that the flexural stresses are accompanied by relatively large tensile or compressive stresses at the middle plane. These membrane stresses significantly affect the bending moment. This lecture will focus on the thin plate with small deflection. Thin plate theory. This theory is also referred as Kirchhoff theory. The basic assumption of this theory: first, a linear element of the plate normal to the mid-surface on the application load should be, first, undergoes almost translation and deformation. Translation means the rigid body translation, and deformation related to the strain. B, remains normal to the mid-surface. That is to say, no shear deformation will be developed. In other words, plane section before bending remain plain after bending. Figure 1 shows this fact, that the section perpendicular to the axis of member will be also perpendicular after bending. The second assumption related to the stresses. Stresses normal to the plate can be neglected. From assumption 1A, linear element through the thickness does not elongate or contract. This is very important conclusion. From assumption 1B, the shearing strains gamma zx and gamma yz will be vanished or be zero. So from assumption 2, sigma z also to be zero. Therefore, the three-dimensional problem will be transformed to the two-dimensional problem. The basic relationships for the plate in bending can be introduced from the figure shown. In this figure, we have a transverse load subjected to this placed upward, and we have a stress distribution on the sides of this element. Here we have the compressive and normal stresses, and also here we have the shear stresses. This element explains how the stresses and moments are act on the plate. If we assume that sigma x, sigma y, and tau xy are linearly distributed, then the moment will be the integration of sigma x multiplied by the arm z, capital Z. This will be followed by also for my, which is the stresses sigma z, sigma y multiplied by arm z, and making integration from at the center of the of the plate, of the thickness of plate, from minus h over 2 to h, which means h means the thickness of the plate. Then the twisting moment mxy will be the integration from minus h over 2 to h over 2 tau xy, the shear, multiplied by capital Z, which means the arm. So we have the twisting moment. While shear force Q will be integration minus h over 2 to h for tau of xz. Also shear y, shear in the direction of y will be integration of tau yz multiplied by dz from the integration from h over minus h over 2 to h over 2. If we introduced u, v, and w be displacement at any point x, y, z, then the rotation of displacement u and v across the thickness can be expressed as follows. U is minus z dw over dx, and v will be minus z dw over dy. As it is well known from theory of elasticity, epsilon in direction of x equal to du over dx, the first derivative of displacement with respect to x. So when we derive equation 7, we obtain that minus z multiplied by second derivative of deflection by dx squared, which is equal to z multiplied by kx. K sub x is the curvature. Also in the direction of y, we have derivative of y or v with respect to y. So it's equal to the minus z second derivative of deflection, w, deflection of plate, to the second derivative to the d of y squared, which is equal to z multiplied by curvature. And gamma xy will be du over dy plus dv over dx, which is equal to minus 2z d2w over dx dy, which is equal to the kz multiplied by kxy. Kxy mean that d2w over dx squared, ky equal to the minus 2 d2w over dy squared, and kxy equal to the minus d2w over dx dy. As it was mentioned above, the problem is reduced from three-dimensional problem to the two-dimensional problem. Therefore, here the forces we have, the vector of forces, which is moment around x and moment around y, and the twisting moment, equal to the h cubic over 12 multiplied by C matrix, C of flexural. This is constitutive relation, constitutive elements for the flexural multiplied by curvatures, kx, ky, and kxy. Or briefly, m moments, mx, my, twisting moment equal to the C matrix multiplied by k curvature of element. So k of element equal transpose, which is equal to kx, ky, kxy. In case of isotropic plate mean that the properties of the plate material is equal in 3 dimensions. So we have one Poisson ratio for all directions and one modulus of elasticity in all 3 dimensions. So CF can be defined as EH cubic over 12, 1 plus mu square multiplied by 1. This is this matrix for the Poisson ratio 1, Poisson ratio 0, Poisson ratio 1, 0, and 0, 0, 1 minus Poisson ratio over 2, which means this for the shear modulus. Therefore, mx equal to the minus dB multiplied by second derivative of deflection over 4 dx plus nu of second derivative of deflection with respect to y and my minus d sub b multiplied by nu multiplied by second derivative of deflection with respect to x plus second derivative of deflection with respect to y, while the twisting moment equal to the minus d sub b multiplied by 1 minus Poisson ratio multiplied by second derivative of deflection with respect to x and y. The definition of d sub b mean the physical properties of the material, which equal to the E multiplied by cubic H over 12 multiplied by 1 minus mu square. The degrees of freedom in this problem will be deflection, rotation, and curvature. Now, we will be speaking about the displacement function introduced to solve or to model a plate. For convergence and compatibility requirements, the deflection function, which is displacement function mean, and normal slope must be uniquely specified along any element interface, so that we have three classes of displacement function. First class is class C2. The assumed function here, the assumed function w of xy has continuous second derivative or curvature. The curvature should be continuous in this class at element corners and inside the element. And the assumed displacement function should be comprised the third degree of x and y. That is to say, x cubic and y cubic with 20 arbitrary constants. The second category of displacement function is a class C1. Here, the assumed function for w of xy should be continuous its derivative should be continuous. That is to say that it has a continuous first order derivative, but may have a discontinuous corner curvatures, so that the degrees of freedom will be w and w over dy, dw over dy, and dw over dx, which means the rotation around x and y. And the assumed displacement function comprises the second degree of x and y. That is to say, the displacement function should contain a terms of x square and y square with 12 arbitrary constants. The third class is class 0, in which the assumed displacement function for w of xy is only continuous, and independent functions are assumed to represent the variation of w of xy and slopes, so that in this case the equilibrium condition between continuous elements according so that in these classes the equilibrium condition cannot be achieved between contiguous elements. Accordingly, smoothing technique is implemented. Consequently, in class C2 shape function, a minimum 6 degree of freedoms should be exist, that are w, first order of w with respect to x, first derivative of w with respect to y, and second order, which is mean curvatures in x and y direction, also twisting curvature, are required at each node, while 4 degree of freedoms, that are w and rotation in x and y, and curvature, twisting curvature, are required at right angled corner, at each right angle corner. Therefore, 24 degree of freedoms are required for a Q4 general quadrilateral element. It also proved It is also proved that taking W and rotation in X and Y as a nodal degree of freedoms will result in discontinuity in the curvature at the corners. Therefore, using C2 or C1 type element will result in a complicated solution or incompatible element. Now, let us go to the modeling of elements with 12 degree of freedoms. This displacement function can be stated in equation 422 with the aid of polynomial terms, Pascal triangle, shown in figure 3. From this figure, one can recognize that how can arrange these terms in displacement function. And this is the four elements, Q4 quadrilateral elements. Now we go for the compatibility to study the compatibility of displacement W and slopes W over dx, dw over dx, and dw over dy, which is rotation in x and in y and x directions along an edge. Consider edge 1, 2, shown in figure 4, in which is assumed to be better, to be the interface, the inter-element boundary between elements A and B, shown in figure. The displacement W along the edge 1, 2 is introduced by substituting y equal to 0 in equation 422. So W will be result in W equal to A1 plus A2x and A4x squared and A7x cubic. That is to say that all the terms of y will be vanished. The slope with respect to x result from derivation of W equation 422 with respect to x, and then supplying and then substituting y equal to 0 will result in the slope with respect to x, that is to say theta of y equal to A2 plus 2A4 plus 3A7 x squared. To determine the four constants A1, A2, A4, and A7, let W1 and the rotation with respect to x and W2 and rotation with respect to y are deflection rotation at nodes A1 and 2 respectively for both elements A and B, mean they are equal. These are the same along the edge 1, 2 by substituting for x equals 0 and x equal L, that is to say can be uniquely specified. Or here the displacement of element A at point 1 equal to the displacement of element 1 at of edge of point 1 at element B. Also this also for the displacement 2 at the node 2. Also the rotation at node 1 of element A should be equal to the rotation of node 1 of element B at node 1 of element B. Also the rotation at node 2 for both elements should be equals. The slope in second direction along the edge 1, 2 can be determined by derivation equation 422 as we say before with respect to y, then substituting y equal to 0. So dw over dy equal to A3 plus A5x and A8x squared plus A11x cubed. Hence, there are four unknowns, A3, A5, A8, and A11, with only two boundary conditions that are the slope at node 1 of element A with respect to y equal to the slope with respect to y of element 1 of element B at node 1 of element B at x equal to 0. The second equation results from equating the slope with respect to y of element 2 at of node 2 at node 2 of element A with the same of element B. So at XOL, then as can be seen, the element is incompatible since we have 4 unknowns with 2 boundary conditions only. Now let us go to the rectangular element with 16 degrees of freedoms. That is to say, using C2 shape function for this element with 4 degrees of freedoms per each right angle node or corner. The displacement function can be stated as in equation 429 by implementing the polynomial result from the product 1 plus x squared plus x cubic multiplying by 1 plus y squared plus y cubic. The resulting displacement function is as follows. From 16 is comprised 16 unknowns. Thank you for listening.